Strike a heavy steel beam, and it immediately vibrates. It is a direct physical reaction to sudden stress. Every structure possesses a baseline dynamic signature. It rings at distinct natural frequencies, dictated by two internal factors: its mass, which resists movement, and its elastic stiffness, which snaps the material back into place. This is a frequency response function, mapping the dynamic behavior of a beam. Each of these sharp spikes represents a specific resonant frequency under normal, unloaded conditions. We normally treat mass and stiffness as fixed constants, but introducing a continuous static axial force modifies these baseline properties, physically coupling the external load to the beam's vibrational response. Apply a static axial load, a continuous inward push on both ends of the beam. This graph tracks the beam's smallest natural frequency as that pushing force increases. Notice the blue line arching downward. As compressive load goes up, natural frequency drops. The beam oscillates slower. The trajectory concludes at the x-axis, where natural frequency reaches exactly zero. How does a constant static squeeze erase a structure's ability to vibrate? And physically, what does a zero-frequency state actually look like? This partial differential equation governs the dynamic bending of a continuous beam. The first two terms capture the standard interplay: physical mass dictating inertia and elastic stiffness pushing back. The third term introduces a disruptive variable, multiplying axial load P against spatial curvature. By mathematically coupling the applied force to the bending geometry, the static environment alters the dynamic capability of the structure. To solve this for real-world applications, engineers discretize that continuous equation into finite elements, turning calculus into matrix algebra. Here is the resulting discrete equation of motion. Inertial forces become a mass matrix, elastic forces a stiffness matrix, and the axial term generates a new block. This geometric stiffness matrix has element-level coefficients, dictating how the beam's geometry changes under load. Look at the mathematical operation applied to it: a subtraction. Under compression, this load physically acts as a negative stiffness. The harder you push, the more this negative penalty reduces the beam's natural elastic rigidity. It assists lateral displacement instead of resisting it. The structure is losing its internal mechanical resistance to bending. To measure this decay precisely, we strip away external vibrating forces and solve the system as an eigenvalue problem. This MATLAB snippet demonstrates tracking these states computationally. A loop runs, simulating gradual compression as the axial load incrementally ticks upward. In this exact solver line, the algorithm recalculates eigenvalues, the natural frequencies, using a net stiffness matrix shrinking with every iteration. The algorithm proves a strict physical rule: an increase in static pressure dictates a proportional drop in dynamic speed. And here is the visual output of that algorithm, the decaying frequency graph. Each time the loop completes its calculation, it drops a new data point. The math builds the physical curve. It starts at the top left, logging the structure's baseline frequency at zero load. As the data descends, the physical reality is a beam turning soft. If struck, it sways languidly instead of vibrating sharply. The smooth descent reveals a structure systematically losing its ability to push back against displacement. Then the dynamic frequency curve definitively terminates right here. At this exact coordinate, the geometric stiffness penalty has perfectly canceled out the elastic stiffness of the beam. The net stiffness drops to true zero. The material provides zero restoring force against lateral displacement. In the real world, a zero frequency state is a failure mode. The column bows outward, and without internal stiffness to snap back, it stays there. By tracking a dynamic decay to zero, we've located the exact point of static structural buckling, when a structure loses its ability to vibrate and collapses.